Hello everyone, welcome to another video from the AI Loop. Today we're going to be looking at Word2vec. It is a technique or an algorithm to convert words into vectors or to give a representation of the words that are being passed as an input to the model. So let's get on to it. Well, what do we need to understand for Word2vec? We'll start off with basically understanding the intuition or the need for the embedding representation. Why do we need a vector representation for the word? We'll start off by understanding that. Well, the first reason, and this is the most basic reason, and it is pretty straightforward, is that when you have a word, let's say we have the word happy and then you have this text, you want to pass it into a machine learning model or a deep learning model, you cannot just like pass the word itself, right? Because the model is not capable of handling text. So you have to find a way to convert it into numbers. Okay, so this is the first reason. And the second reason is that even though you are asked to convert into numbers, you can't just like write any number or represent a particular word with any number you wish, right? It has to make a semantic sense, because if you just like start assigning random words to random numbers, it would not make sense for the representation. So basically whatever that we are writing, so we have the word happy, so whatever numeric value that we are assigning with happy should be able to appropriately represent the word happy, right? So for that we choose a vector. And the way vectors work is that one simple intuition to understand why we need a vector representation is that, let's say I've considered a vector with like 4 positions in this case, and the idea behind 4 positions is that when you have 4 positions in a vector, you could assign 4 different numbers, right? 4 different numerics to each, like different numerics to that particular word, and it helps you explain the word in different dimensions. So here we could consider this as like 4 dimensions. So in the real world scenario, how you would do is you would consider 4 different aspects. Let's take the word color and emotion and life and whatever, like maybe sports, right? Like if I would like ask you to rate this particular word in the aspect of these 4 words, how would you do it? Like, let's say for the color, I don't think color and happy are really associated, so it'd give them a 0.2. Emotion and happy are strongly associated because happiness is an emotion that human beings experience, so I'd give it a 0.9. And life and happy, yeah, human beings experience the emotion of being happy, so that I would give it like a 0.6. And sports and happy, maybe 0.3. So this way I'm able to explain the word in different aspects of the sentence, right? So in different aspects of life. Well, this is not defined, like it's just for an example of taking color, emotion, life, and sports. But basically when you give it to a neural network to train, you cannot really explain the aspects. By the model itself defines different aspects, and yeah, it basically becomes unexplainable. But this is like a small intuition to understand the vector representation for a word. Now that we've understood the meaning or the reasoning behind associating vectors with words, let's look on to the Word2vec technique itself. Well, for Word2vec, the basic minimum requirement is that you have to have like a corpus of text. Ideally it should be huge, and the intuition is that when you have a huge corpus of text, so there's like natural flow of sentences and arrangement of words, right? We want to capture the meaning or the semanticness and the positioning of the words from that corpus, so that the representation is also like is ideal or is in sync with the world, right? This is the intuition. I mean, it is a very rough intuition that I gave, and it might make it very unclear for you to understand, but the requirement is that we grab the sense of the words from the huge corpus. So after having a corpus of text, it basically comes down to 2 techniques. I mean, there are many techniques or like modified versions of this, but the paper introduces these 2. The first one is the continuous bag of words, and the second one is the Skipgram. And how these work, let's look at how these work. I'll explain how each of these techniques work, and I'll illustrate how it goes through a neural network by either picking the skipgram or the continuous bag of words. So for the skipgram technique, let's start off by understanding it through an example. And let's pick an example like I am good to be true. And in this example, let's say this is one of the sentences that we have in our corpus, and we want to train our neural network to understand the sentence and to make sense out of it and give us embeddings. What you would do is you would ideally have a target word, right? Too. And what you would do in this sense, or in any for any sentence in Skipgram, is that you have a target word and you basically ask the neural network to predict the context around it. Okay, this is the idea behind Skipgram, and one small intuition is that Skipgram and continuous bag of words are quite opposite to each other. So having the target word as 2, you would define a window size. Let's say the window size is 3 for now. Okay, the window size should include the target word itself. And what you would do, you would like sample the data like this. You would have input and output, and basically you put 2 as an input and good and B as the outputs, right? So this is the input because this is the target word, and we want to predict the 2 words around it. Because we've taken a window size of 3, we're only considering the words good and B. If you've taken a window size of 5, you would also include words like true and am. Now this is the intuition behind Skipgram. We'll go on to understand the continuous bag of words. Now continuous bag of words is quite opposite to the way Skipgram works. Continuous bag of words really gives you the context and asks the neural network to predict the target word itself. So in this way, let's again understand it by going through an example. Let's consider the word I am the hero, right? So, and let's take the window size to be 3. And remember guys that window size is a hyperparameter that you choose, and it really depends. I'm going to talk about it in a minute, but here let's consider the window size to be 3. So that would be this. So our first window would be this, right? This particular window, because 3 words. And what I would do is that I would have a target word and 2 words that are able to predict the target word. So the will be my target word. So again, let's draw our input or output boxes, and these 2 will be my target words, and this will be the output, like, or the word that has to be predicted by the neural network. Similarly, you would go on to the next window. That would be this one. I'm so sorry it's getting ugly in here, but what we would do is we would take the word am and as the input and ask the neural network to predict the word hero. So this is the intuition behind a continuous bag of words. So one technique is basically giving you the context and asking you to predict the target word, and the other one is giving you the target word and asking you to predict the context. It really depends on case and like the kind of data you have on what you want to represent. So based on that, you would go for either one of the techniques. And about window size, so window size is a hyperparameter that you have to choose to train your model. So the larger the window size, the more the data that you get. And one more thing to observe is that when choosing a window size, it's not like it does not make that much of a difference, but like there are ways where you can try to grab different aspects through various window sizes. It's not like as you shift window size up by 1, you get like a drastically different representation, but ideally, like with small window sizes up to 15 are set to give like one kind of representations, and the window sizes over 15 are set to capture different aspects of the word when compared to the smaller window size. This way we have defined window size 2, and let's look at the example and how like one of the prediction works. Let's consider the word I am the hero again, and let's say this is our target word, okay, and we're having a window size of 3 here. Okay, so let's consider this to be our window size, and so I'll have am and the as an input, right? So ideally what would happen is that initially for every word, so you would have a vocabulary size. Vocabulary size is the total number of unique words that are present in your corpus. So let's say in my corpus I have 500 500 words, unique words. And what I would do is that I would have a table, and this would be the embedding size, right? So how many positions, in how many dimensions do I want to represent each of the word? Let's consider this to be like 512, okay, in here. And what you would do is that you'd want to represent each of the word with 512 positions of vectors. So initially from this, you would take the representations of amp, the, and hero, and how that would work is that you would have it randomly initialized. And basically what you do is you have a neural network. On the first layer, you would be accepting 512 and 512 as an input. So this plus is like 1024 as an input, because you're passing two words, the context am and the as an input, and each of the word embeddings correspond to the size 512. And what you would do is, like, usually in the middle layer you project it to some size that could be like a hyperparameter, and in the end layer what you would do is you would project it back to the vocabulary size. The vocabulary size is 500, right? So usually you have like neural networks, so usually you have like a vector that's of size 1 into 512 here, and then you would pass it through a softmax, and softmax would give you the probabilities of each position, and somewhere in here, maybe here, lies our target word hero. And what you would do is you would have the loss calculated and back propagation all the way, and this way you would go through one example after another until you get through the whole corpus. It can be training expensive, it is actually training expensive, but once you have your model trained, basically what you could do is you could take your, it's basically once your model is trained, you could take your representation and multiply it with the weights. So from the embedding table, whatever you want to represent, like let's say some word here, you would take it and say this is a neural network, you would multiply it with the weights in here, and you would get the output vector. So that's the way, and this is the output vector that particularly represents that particular word. Although this might be unclear, I hope you got the point and the way it works and the techniques before that. As of now, at the present date, with the pace of AI, Word2vec is, it's not really used anymore. These days you would just like take a transformer and input your words, or like even if you want to encode the whole sentence or like a particular word, you just like input it and take the CLS representation, the classification token representation, to represent that particular word or that particular sentence. But it's very ideal and good to know, because this is one of the concepts that revolutionized the way, or the way words are represented. And that's it for the Word2vec tutorial. Thank you everyone for tuning in. I hope you liked the video. Please subscribe to AI Loop. I'll see you in the next video.